Okay, test, test. You guys got sound on that end? Looks like we do. If history is any indication, probably the picture is backwards for y'all. So I'm going to go ahead and swap that around, see if that's better. We read that? Yeah. Let's see if I can turn your guys' volume up just a little bit. Well, it says your volume's all the way up. Okay. So we should be in business now. Can everybody hear me all right?
Yeah, I can hear you.
Yep.
Okay, beautiful. And I can hear you too. And we're reading this correctly?
Yeah.
Yes.
Even better. Okay. So what we're going to do today, we're going just a little bit out of order. I was saying a second ago. We're going to cover section 7.1 today, which is on integration by parts. And then on Friday, Daniel's going to do our first student taught lesson on section 6.4, which is this topic of work, the concept from physics. Integration by parts usually kind of marks the transition into the main first part of the class. So I think of, the chapter 6 stuff and chapter 5 stuff is largely being a warm up, and chapter 7 is being the place where things really get going, because this is the beginning of us talking about a bunch of different methods for integration. Because integration by parts takes a little while to write, I'm going to abbreviate it as IBP often. And what it literally is an antiderivative version of the product rule. So if you take the product rule and you integrate through it, you get the integration by parts formula. I think the play here is just to tell you the theorem. All right, there's an awful lot of functions that you can't differentiate without the product rule. X, e to the x, right? Or any polynomial times sine x or cos x. All of those things we cannot integrate at this point either, unless things are set up just right for us to make a little use of, right? Like we can integrate x times sine of x squared by subbing for x squared. But anything else, unless it works out perfectly like that, we cannot do yet. I'm going to write down the result. And then I'm going to explain it because the notation looks a little bit weird the first few times you see it. So u and v here are functions. All right, think of them as functions of x, which means that du and dv are differentials, right? Like u primed of x dx, that would be du. V prime of x dx, that would be dv. The way we use this is by taking our original integral and kind of splitting up the inside. One part of it we'll call u, and the other part of it we'll call dv. It's called partitioning the integrand. So you look at everything in the integral and you kind of chop it up into two pieces. So those two pieces together form the whole, and there's nothing, no overlap between them. There is a separate version of this for definite integrals. doesn't look a whole lot different. We have integral a to b of u dv on the left. The place where people goof up is they forget to evaluate this middle piece between bounds, or they leave off the bounds on the integral. That's it, right? This is the integration by parts formula, or formulas, if you like.
So the bottom one is the complete formula, or
Well, for indefinite integrals, this. For indefinite integrals, this.
yeah.
So really the same thing. Really the same. I'm going to prove the top one for you, and then you can think of the bottom one as a consequence. I'll prove the bottom one for you, but not not directly, not it's kind of a picture proof that I like for the bottom one. Very nice. It's not fully rigorous. Okay. I'm going to take a quick look at the proof. Let's say that u equal u of x and u equal v of x be differentiable functions. And I mean differentiable in whatever domain you want, right? Meaning that the derivatives exist. By the product rule, we know that u times v all, I'll use the size thing. And by the product rule, if I want to differentiate with respect to x, the product u of x times v of x, I do that by differentiating one at a time and summing. So this is du dx times v of x plus u of x times dv dx, right? If I want to pass from a rule about derivatives to a rule about integrals, integrate on both sides. Let me, just to make things a little prettier, let me write this as b times du dx. So now if I integrate on both sides, integral of the derivative of x times v of x, I'm integrating with respect to x, is equal to the integral of this sum. So done, dx. What do I get on the left-hand side here if I integrate the derivative of some shape?
You just get the integrand itself.
Yeah, if you want to be a sloppy physicist about it, you can be like, the dx's cancel. And then you can say the integral and the derivative undo one another. However you want to get there. I don't, you know, sloppy physicist is not really my style. But I know we see a lot of that in the undergrad calculus sequence. By the fundamental theorem of calculus, This left-hand side is just u times v. U of x times v of x. The integral of the derivative of a thing is a thing. It's the antiderivative of the derivative. On the other hand, over here, again, a sloppy physicist, and I will do sloppy physicist things. I'm going to distribute the dx, split up the integral. This is the integral of v of x times du dx times dx. Plus the integral of u of x times dv dx times dx, cancel the dx's, this is u of x times dv. Now, the notation we use over there, we're just writing u's and v's, right, rather than u of x and v of x. What this says is u times v equals integral of v of x is just u. Right? The only reason I've been writing the of x is to emphasize that these are functions of x. U of x is just u. So the right hand side is the integral of v to u plus the integral of v to u. And now you look at that, and you look over there, and you realize they say the same thing. All right, if I just rearrange this, if I subtract, see, I want the u dv integral on one side. This is equivalent to saying integral. U dv, I leave this guy alone, is equal to uv minus the integral of v. Which is what we wanted to show. There's one way.
Question. So how is u times v equal to, because here, so I'm a bit confused by the fact that the integrand and the, so it's like a v du. That, how visually that doesn't make much sense to me. What is that even saying?
Remember that u and v here are functions of x. So when you see du, you should think u primed of x times dx. So it's just a simplifying notation, right? If I wanted to be very, very careful about it, the idea geometrically, and you don't need to write this down since u is u of x and du dx would then be u primed of x. We learn that du is u primed of x dx. Right, so when I write du, it's a shorthand for u primed of x dx. Sorry, go ahead.
But it isn't u du, it's u dv and v du.
Right.
Does that change things?
So, this, if I want to talk about something like v du, that would be v of x times u primed of x dx, because v is v of x and du is u primed of x dx. So it's just a product of some function and the derivative of some other function. That's how you should think of v du. It's the differential form of v times u primed. So this proof I'll give you is not insightful, right? What we see is that this formula is equivalent to the product rule. What is insightful is a picture proof for this guy, which I'm going to show you, but not before we get a little bit of practice, because the best way to start understanding what this thing does is to just look at what happens when you apply it. So understand if the formula doesn't have an obvious geometric meaning right now. Let's see how we can use it, and then I'll show you the geometry. Give ourselves some context. So there's a bunch of functions that we couldn't integrate before that we can integrate using this thing. I'm just going to write the formula up here. And then our first example. The most natural thing is to take a product of two functions. Something like x e to the x. If I asked you to integrate this last Wednesday, we'd be like, nothing jumps out as working. Maybe you try subbing for e to the x or something like that, but that doesn't work because we sub for e to the x dx would be your dz, and then you still have this x left over, which would end up being the natural log of z, which is like, we don't know how to integrate the natural log of z dz either. But we know, or at least have been told or shown, that integration by parts is logically equivalent to the product rule. And x e to the x is something we would definitely differentiate with the product rule. So it makes sense that we should try the integral version of the product rule on this. And the trick is to partition our integrand into two pieces, or two parts. U and dv. So I look at my integrand here. I've really got three pieces. I've got x and e to the x and dx. And by partition, I mean I could take e to the x dx to be one of those things and x to be the other. I could take x e to the x to be one of those things and dx to be the other. I could take x dx to be one of those things and e to the x to be the other. All right, they have to multiply to the whole thing, and there has to be no overlap between them. I will choose x to be u. And this is not a substitution. I want to be clear about that. That's why I like to use the letter z in my substitutions. I'm not substituting u equals x. I am partitioning the integrand and assigning the label u to that part. I'm going to assign the label dv to everything else. So once you pick one of them, everything else has to be the other, right? That's the nature of a partition.
Why do we call it dv and not like v?
Because it includes a differential, right? Because it includes the dx piece there. It turns out the way you're going to choose this, your dv will always be the part that includes the dx, and these are both what are called differential one forms. So in order to have them be the same type of object, it's not quite appropriate to call this v. The other reason is that you're going to differentiate, right? So look at the pieces that exist here. If we start with u's and dv's, over here I have u's and v's, and then v's and du's. So I'm going to integrate dv to get v, and I'm going to take the differential of u to get du. So it's evocative of what we're gonna do with it. In fact, after you partition, the next step is to complete this little IVP table where we put the pieces that we've chosen.
Does it matter which piece you choose?
It does, and that's one of the main things we're going to talk about today is how to choose U and V. I'll give you a kind of guideline that works for 90% of problems, and then the other 10% of problems you're going to have to be creative and kind of see what works. I'll also kind of give you a way to think about this that's a little bit intuitive. All right, so in our formula you have U's, V's, Du's, and DV's. we chose a u and a dv. So we need to compute from these the pieces we don't have. So I chose a u. I need to know what du is to use my formula. I chose a dv. I need to know what v is to apply my formula. So you start by selecting u and dv. You write those down in this table, and then from each you compute du. If u is equal to x, then du is equal to dx. That part, taking differentials, is the same as you do in a u sub. If dv is e to the x dx, you integrate on both sides to get v. Right? Integrate dv to get v, just like in the volume problems. Integral of e to the x dx is e to the x. Notation wise, I like to put this in a little thing, and I like to label it with letters IVP so my reader can tell what I'm doing. And now you just plug into the formula. So I'll write the whole thing here. The integral of x e to the x dx should be equal to uv minus the integral of v du. So u times v here is x e to the x minus the integral of v times du. That's e to the x dx. You see all the pieces there? The x e to the x, and the first part after the equal sign is u times v. And then you've got minus the integral, and then integral is of v times du, which is e to the x times dx. The miracle, of course, is that the x is gone. Right, my new line still has an integral in it, but that integral is easier than the integral we started with. And that's the first, if you're looking for guidelines, how to choose u and dv, the very first thing that should be on the top of your brain is this integral nicer than the one we started with? If the answer to that is yes, then you've done well. If the answer is no, you're going to go back and try something else. We all know how to integrate e to the x. Not too bad, right? Any questions on this one? Okay. This problem belongs to a class of problems, a larger family of problems. Where you take, your book says early transcendentals on it. What does transcendentals mean?
Isn't it some sort of movement in the 19th century?
There is that. Yeah, there's a few different philosophical groups have coined the term. But in the context of calculus analysis, a transcendental function is a function that more often than not outputs transcendental irrational numbers, right? So if you feed in any rational number to the function of e to the x besides 0, you're going to output an irrational number. Not just any irrational number, but an irrational number that is not the root of any polynomial with integer coefficients. So like square root of 2 is a irrational number. That's what we call an algebraic irrational, because the polynomial x squared minus 2 has square root of 2 as a root. Pi is also an irrational number, but it's what we call a transcendental irrational number, because there's no polynomial with integer coefficients that has pi as a root. Transcendental functions are functions that output lots of transcendental numbers. Another neat feature of those functions is that when you differentiate them, they don't go to 0. Right? Differentiate a polynomial enough times, it will become 0. If you're trying to integrate any polynomial times a transcendental function, specifically sine, cosine, or e to the x, then you should run IVP in the same fashion. Let's look at this guy. Okay, again, if I asked you to do this the other day, we'd be like, shit, oh, this looks hard. But we can do it. Same logic, if you're going to differentiate, the product rule. So we're going to integrate, follow the integration by parts. The reason this worked is because the polynomial piece, the piece that made that integral hard, the x out front, we were able to differentiate it and make it go away, right? So the way Arthur Mathick at MIT teaches this, he says, when you look at your original integral, pick a piece that you want to differentiate and a piece that you would like to integrate. Because what you're going to do down here, since your integral is v du, and you're starting with u dv, your resulting integral will have the derivative of the piece you choose for u and the antiderivative of the piece you choose for dv. So I would like to differentiate the x here because that will make it go away. And I don't mind integrating e to the x because it stays e to the x. If I want to make this integral better, I would like to differentiate the polynomial because it will go from being a quadratic to a linear. And I don't mind integrating sine because it's just going to bounce sine, cosine pairs. So same sort of thing. You have to start with the partition of your integrand into u's and dv's. I'm going to choose for u the polynomial piece. I'm going to choose for dv everything else. And x dx. du. So now we have to compute du from u and v from dv. Du here is going to be 2x minus 3 times dx. And please use good notation here. I don't omit the differential. If you integrate sine of x dx, you get negative plus of x. Table. And we plug into the formula. Now, my integral, which was like this, should be equal to uv minus the integral of dv. That's x squared minus 3x times negative cos x minus the integral of v times du. Negative cos x 2x minus 3 dx. One of the things that you're going to notice, because there's a minus sign in the formula, we tend to get a lot of negatives piling up. You need to be very careful with your parentheses on this problem. Integration by parts demands careful use of parentheses. Let's just simplify a bit. So this is negative x squared minus 3x plus x minus 3x plus the integral of the polynomial out front again, because that's how it was before, 2x minus 3. And the thing we ask is, has the integral gotten better? Not necessarily is the integral done or trivial, but have things improved? And yeah, I would argue that here they have. And it's still the case that I don't know this antiderivative, right? It's not like I can just be like, boom, done. But quadratic times trig, linear times trig. Life is getting better. Any guesses as to what we might try next? Yeah, again, right? If I can take the degree of this polynomial down once by applying the integration by parts formula, I can take it down again by applying the integration by parts formula, choosing u and dv in the same fashion. U, the piece I'd like to differentiate, everything else dv. We're going to run IDP again. Again, taking u to be the polynomial and dv to be everything else. That's usually how we'll do this, by the way. You'll choose u, and then dv is everything else.
And do we just leave that other side of it, the side that's not inside of integral, just sort of leave it there alone and we'll come back to it later?
Yeah, this guy's chilling. He's just going to hang out with us through the rest of the problem. He's going to come down with everything else we do.
Cool.
So you think about these as being done. Okay, if u is 2x minus 3, then du is 2 dx. If dv is cos x dx, then v is sine of x. And you differentiate to go from u to du, you integrate to go from du to v. I've got out front here still negative parentheses x squared minus 3x times the cosine of x, then plus, and I'm going to replace this whole thing by some stuff I like to put in parentheses. Especially if there's a minus out front here, you really need this big open paren to make sure you distribute. So good discipline is anytime you replace an integral in line with an integration by parts terms, you should put in parentheses. U times v. So x minus 3 times the sine of x minus the integral of dv. Again, if there was a negative here or a constant we had popped out or anything like that, we would need to distribute it to everything. Right? If this was a minus instead of a plus, this would be a minus instead of a plus, and it would have to be distributed to this and to this. But there is one.
That's supposed to be a 3 is like 2x minus x parentheses.
Oh, yes. So, thank you. Okay. Just test. Making sure you can. Okay, any questions so far? We're almost done. Sine of x times 2 dx. What's an antiderivative for sine of x times 2?
And could you just take the 2 out and make it negative cosine?
Okay. So the 2 is a constant multiple. We're going to rewrite it like this. And then the antiderivative for sine of x dx is negative cos x. There's a negative here, so I can just make this plus 2 cos x. And that's what we get. There you go. Negative x squared minus 3x cos x plus minus 3 sine of x. Minus, when we integrate here, you're going to get negative cos x, so this becomes plus. Cos x and plus equals the definite. And looking at that answer, you might notice a pattern. Antiderivative of the dv piece times u. And then you differentiate here, integrate here, differentiate this to get here, integrate to get here, and so on. There's a method that allows you to do this quite quickly called tabular integration by parts, where you just kind of make a table with 2 rows. You just keep differentiating here until you get 0. Keep integrating here as many times as is required by that. And arrange things according to a little sign rule. I'm not going to require you to learn tabular integration by parts, but if that was like x to the 20 times sine of x, that's what you would want to do. Right? So if you have a large polynomial times sine, cosine, or e to the x, there are many applications of that.
Either for doing this. Like if you, would you allow like a different?
I would. Yep. Yeah. If you just break out tabular IBP on the test, I'll be like, okay. But I won't give you a problem on the test that requires it. I won't give you something that a polynomial degree is huge. Well, let's go ahead and write down what we just said. If if I had some large polynomial or any polynomial indeed, integrals of the form integral of n nth degree polynomial times sine, cos, or exponential. If you have any sort of sine, it could be sine of 2x or sine of 3x or cos of 7x or cos of pi x or e to the negative x or e to the negative 12x times some polynomial, right? Polynomial of degree n, say. These can all be done with IBP. And kind of following what we saw over here, and I'll look at both of them, right? Degree 1 polynomial times e to the x required 1 run of IBP. Degree 2 polynomial times transcendental right times sine required 2 runs of IBP. A degree n polynomial times sine, cos, or exponential. We're done with IBP. I just want to say n applications. All right, so if it was a degree 3 polynomial, we would run integration by parts 3 times. Degree 20 polynomial, you'd have to run IBP 20 times. And these are not the only things we can do with integration by parts. There are a handful of other functions that might not have occurred to you. Kind of embarrassing, we don't know how to integrate at this point. We think of ourselves as pretty good at integration by the second, third, and fourth too, which is reasonable given what we've been exposed to. Which for a lot of us, it's never occurred. Many of our first thoughts are something related to 1 over x, right? It's true that the integral of 1 over x is the natural log. And it's true that the derivative of the natural log is 1 over x. No. Well, it's true that the integral of 1 over x dx equals the natural log of f of x plus c. It's not true. The natural log x until it's worth. I'm the derivative of you doesn't compare the derivative of me. So yeah, we don't know how to do this one. So took top one with me. Well, I love the inverse tangent function. We don't know how to integrate that. Or any of the inverse string functions. Products of exponentials and trig functions. I don't know how to do any of this shit. And these are pretty common functions, right? I mean, we saw things like x cosec showing up in exams in top one. Certainly, integrating the inverse tangent is something we should be able to do. Similar to this, by the way, integral of inverse tangent is not 1 over 1 plus x squared. The integral of 1 over 1 plus x squared is inverse tangent, but doesn't flip over like that. So these are some things we'd like to get our heads around. I'm going to erase the last two. In fact, we're going to start this with the natural log. The first three there, the natural log, inverse tangent, and inverse sine function, are all functions defined to be the inverse of some other function, right? The natural log is the inverse of e to the x. Inverse tangent and inverse sine are by definition the inverse of tangent and sine. So these fall into a category of inverse functions, and all of those we handle with integration by parts as well. And it's not as obvious. This doesn't look like something I would differentiate with the product rule. So the choice of u and dv here is less obvious. But I do know that if I differentiate the natural log of x, it's no longer a weird function, right? This is an example of a function that is itself transcendental, but its derivative is a rational function. Its derivative is 1 over x. So if I were to swap this guy for his derivative, life gets better, which is a good hint. I should pick this. I should pick this to be u. You might think, well, there's nothing else left to pick as dv. That's not quite true. dx is dv. And this will work. If u is the natural log of x, what is du?
1 over x.
1 over x.
1 over x dx.
Very good. Don't forget the dx. And if dv is dx, what is v?
1? Is it
X.
1?
We're integrating 1 dx, and that gives us just x. You can kind of think of it like this, right? The integral of dv is v, the integral of dx is x.
Ah, cool.
So I've got my integration by parts table complete. Plug into the formula. So the integral of ln x dx is the integral of u dv. Should just be equal to u times v minus the integral of v du. And the du is just x. Du is 1 over x dx. And if that integral on the far right looks too good to be true, well, this makes it. It's nice. It's not too good to be true. It is true. So x times 1 over x is 1. Yeah, like 2 times 1/2 or 3 times 1/3. That ln x times x out here, I like to write that as x times ln of x. It just looks nicer with the x out front. And then you just left with the integral of 1 dx. So that's the integral of dx. And so it's dx is your second of x. This is x ln of x minus x plus c. And that is the antiderivative of the natural log. Not bad, right? Inverse sine, inverse tangent, all kind of go the same way. Now, what I'd like to do now is share with you the rule. The rule for choosing u and dv. This will work on 99 and 95% of your problems. More than 90, I think it's a 90, right?
For this class or general?
In general. 99% for this class. I should say 99% of the problems in the book. I'm going to intentionally expose you to some things that live outside this rule. Really, this is a rule for choosing u. You pick u according to this rule, and then dv is everything else. L stands for logarithms. Are there any logarithms in your integral? If yes, you should pick that for u and let everything else be dv. If there are not any logarithms, you next go to I for inverses. And really, logarithms are inverses. If you wanted to, you could probably just add that. All right, so are there any logs in your integral? If yes, pick that for u and let everything else be dv. If there are not any logs in your integral, are there any inverse functions like arctan, inverse sine? If there are not any logarithms or inverse functions, do you see any polynomials? If there are no logarithms and no inverses, but there is a polynomial function of your integrand, you should pick that for u and everything else for dv. Barring any of those, are there any exponentials? And if there are none of those, look for some code. All right, so they call this the Lipet rule. And you can think of it as a rule for choosing u and dv, but because it's a partition, once you've chosen one, the other is determined. So it's just a rule for choosing u. All right, if you see any of these, make that u, everything else is dv. None of these, just move down the list.
All right, just to clarify, so if you see logarithms, you should just choose logarithms and not anything else on that list?
Yeah, like if this was x cubed times ln of x, then there's both a logarithm and a polynomial. You would pick u to be the ln of x and then x cubed dx to be dv.
Okay.
Well, which time do we have?
Then if you integrated a logarithm, it would repeat itself, right? Like you would go into the same process.
Oh yeah, so if you have like an ln of x or something like that, and you choose that to be dv instead of u, then v would be this thing, so you don't get rid of the log. But if you have a logarithm and you choose it to be u when you differentiate it, it will always become a rational function, which is nice. You'll get rid of the logness by differentiating. All right, let's try this. And let's try it on
We need to be over.
I'll swing it over, yeah. Let's try this on a definite integrals. We haven't done any definite integrals yet. All right, so I mentioned the inverse tangent function is one that we are shamefully unable to integrate so far. Make this nice. No, we'll leave it like this. So inverse tangent, right? But we're going to try to integrate. Also, it's a definite integral, so we'll be using the definite integral version of the formula. You look at your Lipet rule. Do you see any logarithms? No. Do you see any inverse functions? Yeah.
Yes.
So I should choose the inverse function to be u. And everything else to be dv. Everything else in this case is just dx. That's fine. I'll set up my integration by parts table. U is the inverse tangent of x, dv is dx. If u is the inverse tangent of x, then du is 1 over 1 plus x squared dx. All right, the derivative of arctan x is 1 over 1 plus x squared. And if dv is dx, then v is just x. And then according to my integration by parts formula, this is u times v. I'm going to write that x out front because again, it looks better. But now it's in evaluation brackets. And it gets evaluated between those original bounds. We don't have to change any bounds. Remember, this is not a substitution. Minus the integral from a to b, so from 0 to 1, of v times du, which is x times 1 over 1 plus x squared dx. Here's my advice. When you do a definite integral by parts, don't wait to the end to evaluate this piece. You're going to be writing it over and over and over again. And usually it's pretty simple. Oftentimes it's 0. Worst case, it's a number. Right? I would rather write a single number than all this crap. So let's get that out of the way. This is 1 times the inverse tangent of 1 minus 0 times the inverse tangent of 0. What is the inverse tangent of 1? Thank you. Yes, pi over 4. So this is 1 times pi over 4, or just pi over 4, minus 0 times the inverse tangent of 0. Now, 0 times anything is 0. So, but just for fun, what is the inverse tangent of 0?
1.
0. Good. Yeah. I try to harp on this politely but frequently. In this class, we will use a lot of inverse trig. Trust me, section 7.3, it's coming heavy. Shitloads of inverse trig. So make sure you list it. This comes from the unit circle. Okay, so 1 times arctan 1 minus 0 times arctan 0, all that chunk is pi over 4. And then here, how do I do this integral?
U sub or Z sub?
Yeah, very good, very good. So a little substitution. I will use the letter Z rather than U because U is used for something else here. What should I substitute for?
X squared.
1 over 1.
I think all of those suggestions could work. If I sub for x squared, I'll end up with 1/2 integral 1 over 1 plus z, which would require another substitution down the road. If I sub for the whole denominator, then I'll be in the cleanest possible situation. So including the 1 doesn't hurt because the derivative of 1 is 0. So I think it's best to include the 1 now. That's not necessary. Doing that, dz is 0 plus 2x dx. What is the other thing I should do here? Yes, change the bounds, right? Remember on the exams, I do require you to do this, and I'll take off points if you don't. It's not hard, it saves you time, it's good. When x is equal to 0, z will be equal to something that's my new lower bound. When x is equal to 1, z will be equal to something that's my new upper bound. What is z when x is 0?
1.
Good, right? Yeah, 1 plus 0 squared is 1. And when x is 1, 1 plus 1 squared is 2. My new integral goes from 1 to 2. Um, 2x dx is dz. I have an x dx in my integral. So I'd say 1/2 x, 1/2 dz is this x dx. So I'm going to get a 1/2 out. The x dx is gobbled up into the 1/2 dz. And then this piece is gone, this piece is gone, replaced by this and this. 1 over 1 plus x squared is just 1 over z. Finally, an antiderivative for 1 over z dz is the natural log of the absolute value of z. This is pi over 4 minus 1/2 evaluation bracket natural log of z from 1 to 2. So it's going to be the natural log of 2 minus the natural log of 1. What's the natural log of 1?
0.
Very good. Details here if you want them. Absolute value of 2 is 2, absolute value of 1 is 1, natural log of 1 is 0.
Question. It wasn't really talked about much in Calc 1, but when we integrate 1 over, I don't know, z, and then we get ln of z, do we always put the absolute value, or
Yep.
are there times that we don't?
So if you're being careful, you should always put the absolute value. If you want to be sloppy, the only occasion where it would be justifiable to not do that is if you're doing a definite integral and both of the bounds are positive. If both of the bounds are positive, then you can say, oh, well, you know, what I'm really doing there is thinking about that as the area under the positive portion of 1 over x, which is definitely going to be a positive thing, so I don't need to worry. But if you're doing an indefinite integral or an integral where the bounds are not both positive, then you need the absolute values. And the good practice is to just always do the absolute values.
Okay.
And then when you plug in, they'll go over. All right, any questions on this one? Okay, I've saved the best for last. There is a scarier universe of integration by parts problems, called looping integration by parts problems. So the majority of IBP problems out there, 1, fall into this LIPET scheme. 2, in some sense, are done by reducing your integral to an easier integral and then
Get
applying
10 to the right.
already knew. I'll tell you guys.
Thanks.
So most integration by parts problems, the vibe is you apply the IBP formula after making the appropriate choice of u and dv some number of times, and you end up with an integral that you eventually can do by u sub or some method that we learned in Calc 1. It is also possible to use integration by parts to turn an integral problem or an antiderivative problem into an algebra problem. This is the example I usually use to introduce this concept. They're called looping integrals. The idea here is that I'm going to apply integration by parts some number of times. I'm going to get out a bunch of like u times v looking pieces, but eventually at the end, I'm going to get my integral back. And then instead of like solving the integral, I'm going to solve that resulting equation. My integral equals a bunch of shit minus my integral. We just add my integral over here and then divide by 2. It feels like magic the first few times you see it. So this is what's called also, this function is a special function, e to the negative x cos x. It's called the damped harmonic oscillator. You see that thing on the door there at the top? The gas piston is called a dash pot. And what it does is it keeps you from being able to slam the door, right? If you've ever walked angrily out of a 7-Eleven and tried to slam the door, it's like, won't let you do it. If you put one of those things on a pendulum, big heavy swinging pendulum, it will dampen the oscillations, right? The pendulum might swing large at first, but then the back and forth motion of the pendulum is damped. The graph of this function, e to the x cos x, sorry, e to the negative x cos x, looks like a cosine wave, but it's dampened. The e to the negative x wants to go to 0. The cosine just wants to oscillate from -1 to 1. So if you take something that's bouncing back and forth from -1 to 1 and you keep squishing it down by multiplying by this rapidly decaying exponential, you get a curve that looks like this, which is your damped harmonic oscillator, right? Here's your pendulum swinging just less and less each time. So integrals of functions like these are very important in physics. You look at a satellite that's falling into its orbit and you crash into the planet straight on from the side. Yeah, harmonic oscillator. Like lots of these exist in the world. Integrating, it's kind of a pain in the ass. And there is a nice trick for this involving complex numbers, if you know Euler's identity. But it's one of the standard things I have to teach you. So it is an integration by parts thing. Which means you have to start by choosing u and dv. And the truth is this, it doesn't matter, right? You can use the Lipet rule if you want. In Lipet, exponential comes before truth, right? There is no logarithm here. There's no inverse function here. There's no polynomial function here. Oh, but there is an exponential. So I should choose him to be my u and everything else to be dv. It will work. Compute du and v from these. The derivative of e to the negative x is a chain rule derivative. It's e to the negative x times -1. So that's negative e to the negative x and then dx. Integral of cos x dx is sine x. Okay. If I apply my integration by parts formula with this table, I get u times v, that's e to the negative x sine x. Minus the integral of v times du, which is, I'll write it as negative u x sine x dx. I'm just choosing to bring the exponential out front because it looks nicer. The negative here can pop out. And I get plus the integral of the negative x sine x dx. That's one run of integration by parts. And remember what we said at first, we should ask ourselves, are things improving?
Not really.
No, not really.
It kind of looks very similar, right? All I've done is swap the sign for a cosine for a sine. But what that means is if I do it again, the sine will turn back into a cosine and I will get my original integral back. And that's actually a good thing. That's why we call it a looping integral. Very important here, if you pick the exponential to be u the first time, you must pick it to be u the second time. If you swap these, and in your second run, do the trig for u and the exponential for dv, then you will end up just undoing what you did. You get 0 equals 0, which is not useful. So when doing integration by parts twice, make sure that your second run through, you do something other than undoing your first run. Specifically with these damped harmonic oscillators, if you chose the exponential to be u the first time, choose the exponential to be u the second time as well. The derivative of e to the negative x is still negative e to the negative x. The antiderivative or an antiderivative of sine x is negative cos x. Pro tip, you can actually pick v to be any antiderivative. All right, so if you look back at the inverse tangent problem, I could have picked v to be x plus 1 instead of just x. That is an antiderivative of dx. Sometimes it's useful. There's a good black pen, red pen video on that if you're familiar with black pen, red pen, the YouTube channel. All right, applying the IBP formula one more again. Here's my second IBP. We have this piece coming along to the right, e to the negative x sine x. Plus, now I'm going to replace this integral here by his equivalent expression through integration by parts, which is negative e to the negative x times negative cos x. That's the u times v from the second IBP. Minus the integral of v du, which is negative cos x times, this e to the x, this piece is positive. I wrote this as negative the first time, so it's positive. U times v minus the integral of v du, and that's what both will do. Again, it's entirely possible there would be a negative here or a constant that I popped out from here. So anytime you replace in line a piece, an integral by its multi-piece IBP equivalent, please put it in parentheses. I'll tell you one classic way that I make this problem just a little bit harder in the homework. Like a 2 here, like a 5 here. When you do your derivatives and antiderivatives in the table, you're going to get things like 2's here or 1/5 here. And then you need to carry those constants very carefully through the problem. Right? That would lead you to something like 5/2 right here, which would need to be distributed over these. So just be mindful. Carry the constants carefully. All right, we got some negatives to clean up. No constants to really be careful about. I'm working on a board, so I get to do this. You have to write a fresh line. Here's a positive times a negative. Minus negative x plus x. Negative times negative here is just positive, and I'll write it. So cleaning up, this is what we get. You notice as I solve these problems, I always write a chain of equal signs, right? My original problem equals this stuff. What I'm saying there is literally this thing is equal to this stuff. Let's encapsulate that in one line. I still have not evaluated this integral. But this is the same as this. So if I called this like z, then this would be z equals all this shit minus z. That's an equation I could give to a 10th grade student. There we go. No, just add this over. Let's do it. If I add the integral from the right to both sides, then over here I'll have this integral plus itself, which is 2 times that integral. And on this side, I'll have e to the negative x sine x minus e to the negative x cos x. At this stage, we start writing the plus c because there's just an integral on the left. There is no integral on the right. Divided by 2. E to the negative x sine. All that says. E to the negative x over 2. And x. This is x, capital C over 2 is still this capital C, right? Arbitrary constant is arbitrary. That's it. And you can verify by differentiating this that you do get e to the negative x times cos x. It works. Again, the way this is made challenging, and it really is challenging when it's done, is by throwing a constant into one or both of these. And there will be something like that in the homework. I have to. This is just sort of the easiest version that I can show you as our first looping integral example. If your brain feels like it's melting, here's the thing to do. Come back to this line and label this integral as I everywhere it shows up. Then solve the equation for I. But I equals e to the negative x sine x minus e to the negative x cos x minus I. You add I to both sides, you get 2I equals e to the negative x sine x minus e to the negative x cos x. If there was a minus 5 times this integral here, this would be a 5I. And when you add it over, you would get not 2I, but 6I. So be careful with the constants. Don't assume that it's always going to come out looking exactly like this. You really do need to pay attention. But it does always work in this fashion. You run integration by parts some number of times. Your original integral shows back up. You better hope it shows up with a negative sign. Then you add it over. All right. We are right at the edge of time. I got to rush home to teach class at 11, so I am going to leave it here. I'll leave the stuff on the board if you guys want to look at it. My Zoom people, take a screenshot because I got to shut the computer down before I go. I've gotten honors project and student teaching stuff from a lot of folks, but not from everybody yet. So please send that stuff to me as quickly as you can. I'll have an office hour today, 1 to 2, tomorrow from 11 to 12. And,
where can I find the full video?
So that's the thing. So I don't really have time to stand here because it takes about 20 minutes for this video to convert and then like another 20 for it to upload to YouTube.
Okay.
I will be coming back to campus Thursday at 1 p.m. for a math team meeting. I can try to get down here and convert the video then. The better move here is to go to my YouTube channel and look for Calc 2 Section 4 videos. Those will also have this and I will post those there. Also, if you look in our modules, I have some stuff for looping IBP.
Thank
Okay,
you.
take care, guys. I'll see you next time.